space of a matroid. So moduli space is somehow a classifying space where you have a geometric object where every point carries some information and some, in our case, the representation of a matroid. The plan for the talk is to give a brief motivation introduction to matroids. As I understand, most of you have seen a matroid before, so it'll be pretty brief. And then we're going to move on to the algebraic definition of the moduli spaces, see computational examples, and finish off with applications of the computational techniques we'll present. So, matroid, you should think of a matrix. So let's just define the matroid by an example. Let's look at a matrix. And let's look at the matrix, which looks as follows. Here we have a 3x5 matrix, let's say with the entries are rational numbers. And the matroid is supposed to somehow capture which of the columns are linearly independent and which are not. So let's say that we get a matroid, which I denote by M of A, the matroid realizable by that matrix, and it is a pair E, B, a ground set and a set of bases, where the ground set is the set of columns, so 1 through 5 in that case. And the bases are all maximally collections of linear independent columns here. So we see that almost all columns are independent except for two pairs. So the first, second, and fourth, and the first, third, and fifth column is dependent. So it's just all triples except these two. So 1, 2, 4, and 1, 3, 5. And this is kind of essentially what happens in general. So you have a matroid is a pair of a ground set, a finite ground set for me, and a set of bases which capture the maximally linear independent columns. And the axioms for these bases are some basis exchange property, which we know from linear algebra. So that's my kind of motivation and start for matroids. These are by now classical objects in combinatorics connecting many areas, such as algebraic geometry, optimization, and whatnot. And here we already see the connections to linear algebra. A second motivation comes from graph theory. So probably most of you know it, but let's just write it out because we're going to see it again later. So we have a pair, a graph, set of vertices, set of edges, undirected graph. We get a so-called graphic matroid, which is MG, where the ground set are the set of edges and the bases are the maximal acyclic subsets of the edges, meaning the maximal subset of the edges which do not contain a cycle. Maximal acyclic subsets of the edges. So we can do an example to this example, namely we can look at the graph, the complete graph on 4 vertices, the K4. We see it has 6 edges. I want to label them as follows. The other one, 1, 2, 4, 3, 5, 6. And then we get the MK4 is the graphic matroid of the complete graph on 4 vertices. It has the ground set 1 to 6. So we see it has 6 edges. And the bases are, again, almost all triples except for the case when we see a cycle in the graph. So it's a E3 minus, here we see a cycle 1, 2, 4. It's the outer cycle. 1, 3, 6. And then 2 more, 2, 3, 5, and 4, 5, 6. So far, so good. Let's move on. Let's formally define what it is for a matrix to be representable. It essentially means that we can write down such a matrix and that the matroid is reduced by this matrix. But let's just write down a definition because that's what we're going to use. The main thing we're going to use in the talk. So we take a matroid pair EB, ground set of bases, or some rank R, meaning that all bases are of size R, and we fix a field F. And then we say that M is realizable or representable over that field, over F, if we can find a matrix, if there exists an R times E matrix. So it's a matrix having R many columns, rows, and the columns are indexed by my ground set E. I want to denote it by A, such that for all subsets S, my ground set with the size of S is R, we have that the minor of a matrix A on the subset S is of rank R if and only if the set S is a basis of my matrix. So that's not so crazy. So in particular, this is a representation matrix of the matroid, of that matrix. And again, we can also do the same thing for the graphic matroid MK4 we've seen here. MK4 need to take a 3x6 matrix. So let's take the following matrix. So that should be a representation matrix of that matroid over every field. So whatever field you want, you can take that matrix, and that will be a realization. Why? Because essentially we need to make sure that these cycles, that the triples corresponding cycles correspond to non-invertible minors. So 1, 2, 4, for instance, is indeed a minor of rank 2, and it's not a full rank. All right. So let me just say that our intuition for matroids comes from the case of the realizable matroids, but asymptotically, almost all matroids are not realizable. So if you count the matroids of size n which are realizable, and we count all matroids of size n, then the fraction tends to 0, meaning that if for large enough matroids, if you pick a random matroid, it's almost surely non-realizable in that sense. So that's the introduction. So let's move on to the second part, the modular space part. So the goal is to build up a space where every point is such a possible representation matrix of a matroid. And we want to do that by defining a classical object in algebraic geometry, namely the Grassmannian. So it's denoted by GR DN F, and it's supposed to be the space of d-dimensional subspaces of F to the n. So it's the space of d-dimensional subspaces of F to the n. So at first it's just a set. So every point in the set is some subspace of my vector space F to the n, but it is much more than a set. It's a nice variety, and one way to see that is via the so-called Plücker embedding. So there's an embedding of GR DNF into projective space of n choose d minus 1. So what do? We take our subspace V and we map it to the so-called Plücker coordinates, PS of V for all S D. So what is that supposed to mean? Well, if we have such a subspace, we can assume it, we can write down a matrix, a D times N matrix, where the row space of that matrix is exactly my subspace V. And then these PS are the determinants of the minors of that big matrix, which generates my V. I collect all these minors, I write them in one big vector. So that's the length of this vector, because I have N choose D many choices here. And that's the so-called Plücker embedding. All right. So that's one way to give that the structure of a projective variety. That was part A. Part B, I want to talk about the stratification of this Grassmannian. Well, this vector of these Plücker coordinates, all of them are non-zero. So we know that they can't all vanish because some of them must be non-zero. But which ones we don't know. And my point is that the pattern of vanishing and non-vanishing of these Plücker coordinates actually induces a matroid. And that's what I call the matroid stratum. And it's what we're going to define next. So let M be a matroid. Now assume that the ground set is just the set 1 to N. Be a matroid of rank D, realizable over F. Then the matroid stratum is the following. It's just the subset of the Grassmannian where these coordinates vanish if and only if the subset is not a basis of the matroid, meaning GR M F. So these are the elements in the Grassmannian where I assume that the PS of V is non-zero if and only if my subset is an element of the basis of my matroid. So in other words, again, so we have this vector, and so the non-zero entries in this vector of these coordinates are exactly at the positions for the bases of my matroid. And since any such matrix defines a matroid in exactly that way, we see that every element in the Grassmannian belongs to exactly one piece of my kind of stratification of the Grassmannian. So this means I cut up my big Grassmannian into many disjoint pieces, namely the collection of all these smaller matroid strata. And the largest piece here is the uniform, the start of the uniform matroid, where all of these entries are non-zero. All of these Plücker coordinates are non-zero. So feel free to ask questions, of course. So lastly, the last piece of definition, then we're already at the moduli space. Here, if I have such an element in the Grassmannian, I have this matrix whose row space represents my subspace. I can, of course, scale the columns of this matrix. If I scale a column of the matrix, the subspace changes, so I move to a different point in the Grassmannian, but the matroid does not change. So the vanishing and non-vanishing of these Plücker coordinates does not change, meaning that by scaling the columns of these matrices, I stay within the same matroid strata, meaning that there's an action by the torus, by column scaling, on that matroid strata. So there is an action of a torus. So it's F star to the N, where every coordinate here acts on one column of my matrix representing the subspace. On on the matroid strata. And so now I define my modular space of matroid to be just the matroid strata modulo this torus action. So the realization space or modular space of M denoted by RMF is the matroid stratum modulo this torus action. And so that's the main definition. And for the rest of the talk, I'd like to discuss that space in several examples. Exactly. My next point is when the next proposition answers your question, hopefully. So this is just some quotient for now, but it is much more. It has the structure of an affine scheme. So the proposition
on its quotient.
For me, it's just the quotient of that space by this torus, by this group action.
Topologically speaking, that it happens to be an affine scheme.
I think so, yes. Yeah, I don't want to be fancy here. Just think of it the group action. I think that you model by this quotient, and yeah. So the proposition is that space I constructed in that sense is in fact has the structure of an affine scheme. So R F is an affine scheme, and I want to give you a sketch of how to construct the coordinate ring of that scheme. So the ring. So first of all, without loss of generality, we can assume that the first D element are a basis, so that 1, 2D form a basis of M by just relabeling the elements, and that just makes it easier for our description. Secondly, I want to consider a big polynomial ring where I have variables xij and I for the column goes from 1 to D, and the J index goes from 1 to n minus D. And then I consider a huge matrix where I have a identity matrix in the front, and then I just have these variables. So I have this big matrix where in the front I have the identity matrix, which is good because I know that the first D elements form a basis, so they should be invertible. And then in the bottom part of the matrix, I just wrote the invariants of the variables of my polynomial ring. So I need one more simplification map, which essentially should take care of this torus quotient. I want to define a ring map. And what should that do? This is a ring map sending one entry in every row and every column of A to 1. and also many to 0, and the variables to 0, which are forced to be 0 by the matroid. So for instance, here in the graphic MK4 matroid, it's of the same shape where we have this identity matrix in the front. And we know that 1, 2, 4 is not a basis. So the column 1, 2, 4 should be of rank 2. This means that this entry better has to be 0, because otherwise it will never be of rank 2. And these are exactly the type of situation we want to take care of, kind of want to model with the zero images here. That's a bit vague, but that's basically the idea of what should happen. And if we have that, then we want to define two subsets of this ring. One is an ideal. So first we look at the ideal IM. What it is, well, it's the determinant of AS, where S is not a basis of the matroid. And we need to apply this pi m. And then we take the ideal generated by these things. So these are, I have my matrix A. I look at the columns indexed by S, where S is a non-basis of my matroid, meaning that I know that these minors have to vanish. That's why I collect them in this ideal, but I also apply my projection map pi. And secondly, I want to have this UM, which is kind of the same, but need to be a bit careful. I do look at the opposite. So I look at the one which do form a basis. I know that they must not vanish. The only tricky thing is this is not an ideal. I want to view that as a semigroup. So because multiplicative semigroup, yes. Because if we know that two of these things do not vanish, I don't know that the sum vanish. The sum might vanish, but the product then must not vanish. And then the coordinate ring is just the following. Of our MF is, well, it's just we take the projection of our ring, we mod out by that ideal, and we localize that semigroup. And that's it. So this, even though we can compute this is an explicit thing which we can compute and which we will compute. Nevertheless, these spaces are somehow bad. So these facts, the spaces RMF are arbitrarily bad. So what do I mean? It means that whenever you have your favorite singularity, then there is some rank 3 matroid where your singularity essentially appears within this realization space. That's what is called Meff's universality result, or Vakil's, later on extended by Vakil to Vakil's Murphy's law in algebraic geometry. And even though, so it's known that it's no way to classify these realization spaces, so that they are somehow tame, there was not really an example known up to last year. So the first example of a matroid where we see some singularity at all is for a matroid of rank 3, size 12. So the smallest matroid with Rm F singular in rank 3 has 12 elements.
Is RMF singular if and only if the whole matrix struggle was matrix locus is singular?
That I don't know. I'm not sure.
But the question is, if we already know that sort of this GRMF is singular, is this RMF singular and vice versa? Is this like equivalent or is it just?
Don't know.
Depends a little bit on how the torus acts. So I also asked about
Yeah,
the
okay,
question
okay.
about.
Don't think so. There's a paper by Dante. There's a paper.
Yeah, I'm talking about the paper by Dante and Dan Curry. So, but they talk about the RMF, the small space I'm talking about, and they produce an example where this small thing is singular.
Is that word about dimension?
Not really. I mean, so it's you can't even combinatorially characterize when it's empty or not. So the space being empty means that it just tells you if the matroid is realizable or not, and there's no combinatorial characterization of realizable matroid in that sense. So it's also in particular, and this tells you if the space is non-empty or not, and also for if it's non-empty. I mean, there are maybe some upper bounds or lower bounds on these dimensions, but it's impossible to predict just looking at the matroid what's the dimension of this thing.
How much does this depend on the field? So obviously, the reliability depends on the field, but for example, smoothness or so.
I don't know. We're going to see this example in the computer, and I think that it will be like kind of generically singular over most fields. Maybe there are some fields where something strange happens. This could be possible, and then it's somehow just the space degenerates to a point or something like that, which is then smooth or so. But I don't know more than that. Okay, so you've already asked a lot of questions about examples or about kind of how the space looks. So this concludes the first part of the talk. And now I'd like to show you computations and examples. For that, I'm going to switch to slides. Are there questions in the meantime while the projector is hopefully loading? But there's no...
I don't think it's wrong. Just press the red button again. And maybe not, then right away.
Ah. Okay.
So this said also that we were talking before saying that Dante was interested in this question about what is the sort of combinatorial reason why the singularities appear. So we think also now nothing can be said in that regard.
Well, maybe there's a way to kind of see some structure in his examples which kind of ensure that some singularity appears, but I think it's hopeless to kind of have some combinatorial criterion to say if this happens, then the matroid is singular or something like that.
Let's say, like, for example, restrict to a class of matroids and say at most certain type of singularity appears or something like that. Yeah.
Well, yeah, I mean, if, for example, graphic matroids, then it's always just a point. So they are always projectively unique in the sense that this space is always a point, so it's always smooth, but so that's kind of trivial.
What type of singularity appears in this word?
Yeah, you're going to see this in 5 minutes, hopefully. So should I press anything else or just wait? Okay. And how do you get rid of this top right thing? Or is it doesn't? Okay. Okay, great. Okay, so now let's go to the yes. Let's go to the demonstration, the software demonstration part. Do you mind if I move? You want me to sit there, or what do you want?
I mean, I don't know where you want to sit.
I
mean, I don't want to sit off the camera.
I see. I can sit down because I need to press these buttons, and then I'll stand up and again in a bit. So I want to talk about this module in OSCAR. OSCAR stands for Open Source Computer Algebra Resource, and it's a new computer algebra system which aims at combining and extending existing packages, NTIC, GAP, Polymake, and Singular. And so now it's a bit cut off. Sorry. Better, slightly. Okay, so this is a module developed by Dan Curry, Benjamin Schröter, myself, and it aims at just the basic about matroid constructions, the showering of a matroid, and the realization spaces. And today I mostly want to talk about these realization spaces. Yes. So let's look at the example of the complete graph K4 we've seen in the beginning. We can construct the cycle graph, and here's the realization space. So here we see that the output is a matrix where we just have one variable. So after this pi map, there's just one variable left. But we also see that there's an ideal telling us that x plus 1 should be 0. So essentially x should be -1. And avoiding the 0 loci of some polynomials, meaning that x should not be 0. But we can use that x plus 1 equals 0 to get rid of x. So that's what we by default do if we don't set simplify to false. And so if we do that, then we indeed find the -1 here. And then we just see that the space is just one point, and over this one point, we just see this one matrix, which up to permuting the column and maybe some signs we've seen before in the book. And here also to your question about different fields or characteristics, here's the Fano matroid. It's a well-known example. And the realization space tells us it's again just one point, one matrix, but this time we see that the 2 should vanish, meaning that 2 should be equal to 0, and that just means it's only realizable in fields of characteristic 2. Because here we compute this over the integers so that we can compute this realization space over all characteristics at the same time, and we find here that it's only realizable in characteristic 2. So we can also ask that directly, and then get these answers. That is true in characteristic 2, but false in characteristic 5. And for the non-Fano case, it's the kind of the dual matroid where the kind of opposite thing happens. We again see that there's one matrix, but this time it says avoiding the 0 loci of 2, meaning that it's always realizable as long as 2 is non-zero, meaning that we just have to be in a field of characteristic non-2. And so we can again ask if it's realizable over 2, false, and over 5, true. Here's another example, is the non-Pappus matroid. And here it's the first example where we don't have any realization at all. So over all fields, the space is empty, we've been talking about. And that's essentially due to any realization would violate the theorem of Pappus. And again, we have a dual thing, which is the so-called Pappus matroid. And here's the first example where we see something positive dimensional. So we see here 2 variables. So we have no ideals. So the space is A2, where we need to take out a bunch of polynomials, so a bunch of curves. So it's just A2, the plane without some curves. And whenever we pick a point in A2, which does not happen to lie on these curves, we can plug in x1, x2 in this matrix, and that is the parameterization of these realizations.
Will you say something about how you compute all the computations for it?
Well, it's more or less like this. There are some tricks to make it feasible, but it's essentially this recipe here.
For example, on the previous slide where you But you didn't specify any field?
So they did not specifying the field means that we don't take f here, but just the integers. And then we compute Gröbner basis over the integers. And do all of this over the integers. And so you have an ideal over the integers, which you can then specialize to some characteristic, to f5 or something. And if this ideal over the integers is already 1, this means that there's, whenever you specialize, to which field you specialize it, you will never get a solution to this system of equations. Well, that's the idea we want to do. Okay.
Realizability over R?
We can't check that. But it tells us that it's not, it tells us that we cannot realize it over an algebraic closed field, so also not over R, but we cannot check for realizability over R so far. And so here we see, we saw that the Pappos matroid, it's A2 minus some curves, but we can also ask for one specific point, and then we should get, here, we get one particular realization. If we just want to have one, and we don't care where we are, but we just want to have one, then we get here one realization of the Pappos matroid with rational coefficients. We can also try if the same things happen for F2, but then it tells us there's no realization of the Pappos matroid in F2. So maybe we try again with a larger field, so maybe F4. And here indeed we find a realization in F4 where we take the field extension defined by that irreducible polynomial, and then this gives us the realization of Pappos matroid in F4. Lastly, there's the affine geometry, which is a nice matroid on 9 elements. And here we see for the first time also a non-trivial polynomial appearing. In the sense now we need to have a solution to this polynomial, and it's over most fields this will be irreducible. So we have two solutions to this polynomial, and whenever we plug in one of the two solutions in our matrix, we get the realizations of this matroid. There's a database of matroids, which is very useful if you have a conjecture about matroids. You can use the database. It has all matroids up to 12 elements in rank 3 and 10 elements in rank 4. This is already quite a lot. And we can access this matroid database by, for example, we want to look at all matroids on 9 elements, rank 3, which is simple. Then we see that there are 383 in the database. Now, for some reason, we are only interested in those which are realizable over a field of characteristic 0, and we can just filter that database. And in a few seconds, hopefully, we should see an answer to that question. And there we just lose a few matroids. Yeah, 370. So we had 383 before, so we lost 30 matroids which are not realizable over characteristic 0, but we can, if we are interested in for only complex matroids, then we can take these 370, for instance. And here we come to the example of Curry and Luber. These are the non-trivial rank 2 flats of their matroid. And here's it's a matroid of rank 3 on 12 elements. And the realization space looks like that. It's a bit messy because it's a bit larger, but the important thing is that ideal. We're going to focus on that ideal. It's a hypersurface defined by this one equation. But the point is that this equation is not irreducible because we can decompose it into already two components. Yes, so that's degree 4. It's non-homogeneous degree 4, but it decomposes into two components, one conic and one, this is also decomposes into two lines. And so where these two components intersect, there's the singularity of that matrix, of that realization space. So that's regarding the question you asked before. Okay, so this concludes the software demonstration part. And the third part, I'd like to talk about applications of this. So do you have questions on these computations. Yeah.
So this is not always irreducible. It can be a reducible space, the realization space. Or
Yeah, here it's reducible.
is it always connected?
Also no, I think.
So you call the space a moduli space. Does it parameterize anything?
Yeah, I mean, okay, I'm not an algebraic geometer, but in my mind, it parameterizes the realizations of the matroid. So if you move around that kind of this curve, then
Realizations up to sort of rescaling.
up to rescaling, yes. So or if you kind of view the columns of this matrix as the defining the hyperplanes. So these are hyperplane arrangements, and then it's kind of like whenever you move around that space, you get a arrangement of hyperplanes defining the same matrix in that sense.
In this example, you also have to avoid some locus of.
Yes, but they check that the locus, the singularity is not cut out by the things which you have to remove. Yes. Okay, so now, yes, for the last part of my talk, I'd like to talk about applications. Readable, yes. Okay, so now two applications of this technique. The first is on operators on line arrangements. So Xavier Rouleau, who is an algebraic geometer in Angers in France, he introduced the operators lambda and m on arrangements in P2. So P2 just means projectivized versions. So these are realizations of rank 3 matroids for 2mn. And what it does is, if you have such an arrangement, he collects the m points. The m points are the points where exactly m of the lines meet. And then he draws a line, this lambda or nn gives you a line. Whenever you find exactly n collinear points of these m points. That's a bit of complicated, but let's look at an example. Here's an arrangement of 5 generic lines, so meaning that they only intersect in 2 points. So the m is always 2 in this case, because all points, in all intersection points, there are only 2 or exactly 2 lines meeting. So lambda 2, 3 is easy, because lambda 2, 3 are the lines which contain exactly 3 of these 2 points, but you see there are none, so it's empty. Lambda 2, 4 is also easy, because when do you see exactly 4 of these 2 points? Well, these are the original lines, so lambda 2, 4 preserves the arrangement. So only the new case is lambda 2, 2 is where you draw a line when you see exactly 2 of these 2 points. So for instance, you would add that line, or you would add that line. So you can count that there are 15 of these lines, and meaning that the lambda 2, 2 operator, kind of this arrangement diverges and gets larger and larger. At least the first step is at least like that. So the goal is to find arrangements where this lambda, let's say the matroid underlying this lambda and m of A defines the same matroid, meaning that this lambda operator moves you around in that realization space. So you hope for that there's some interesting dynamic moving in this lambda on that space. Maybe there's some periodic points, maybe there are points where it diverges, maybe there are points where this lambda is constant, but at least you want to hope that you find arrangements where this lambda preserves the matroid structure and you move around in that realization space. So that's what we'd like to study. In the first work of Rouleau, he found an arrangement of 6 lines where it has a one-dimensional realization space, and this lambda 2, 3, which we've seen before, was empty. In that case, not empty, it acts non-trivially on that one-dimensional curve. So it's a one-dimensional space where we have to remove some points, and this lambda 2, 3 has some interesting action on that one-dimensional space. And interestingly, these 6 lines, they also meet in only 2 points, so there are 15 double points. And the 15 double points, they were known before. This is a prominent Abe, Kunstcover, Nuno, Zava arrangement. It's a prominent example. It's a one-dimensional realization space. It's free, but not recursively free. So I don't want to define these notions, but just to say that these are prominent examples in the arrangement community, which were surprisingly found by studying this lambda operator, or refound by Rouleau using this lambda operator. So that's the start of our collaboration. we want to start, we're looking at these regular k-gons. So here we see that the 7-gon, the black lines form a regular 7-gon, and the blue lines are the lines of symmetry. But I drew this funny circle in the middle, and I do that because I want to, in my mind, deform the blue lines that they only intersect pairwise, so that they don't, if I draw it like that, they will all intersect in this one point in the center, but I don't want that. I want to deform these blue lines so that they meet in the interior just pairwise in 2 points and keep the matroid structure and apart from this in the center intact. And that's what I call the matroid MK. And what we proved is that if we do that, then this realization space MK is 2-dimensional, it's singular, and some lambda for the right choice of N and M acts non-trivially on this 2-dimensional surface.
MK only the blue lines?
No, MK is the blue and the black lines. So it's, yeah.
It doesn't matter how you deform it.
Well, just combinatorially. I just mean that I just combinatorially my matroid input that these blue lines meet a pairwise. I mean, every blue line meets every other blue line in 2 points. And I don't know anything else about this. So if I wouldn't do that, if they would all meet here, it's a simplicial arrangement, and the moduli space or the realization space of this thing is just a point. By taking this deformation, by ensuring that these blue lines do not meet all in 1 point, I get an interesting realization space, namely I get a 2-dimensional surface which is singular. And for this k, for the heptagon, for the k equals 7 case, I get this strange-looking quartic equation, which is singular. But Xavier got really excited about this. He's an algebraic geometer. To me, in combinatorialist, it doesn't mean much, but he got excited about because it's a K3 surface, and it is a prominent surface in algebraic geometry, namely it's the elliptic modular surface. So the elliptic modular surface is a classical object introduced by Shioda, and it's the modular space or the compactification of the modular space of triples EPT, where E is some elliptic curve, P is a point on that curve, and T is a generator of cyclic torsion of order K. So you take these triples EPT, you lump them all together, hit the compactification, and that's somehow the elliptic modular surface. And the interesting observation is that for K equals 7, this thing agrees with the one we computed as the realization space of my matroid. And then we kind of tried to prove it, and we managed that that's indeed always the case. So we obtained this commutative diagram where here's this elliptic modular surface. And what we do, we take this point P, we add this cyclic K torsion generators, we apply lambda, we take the union, then we have something of 2K, and we prove that apart from some closed exceptional locus, this is always a realization of our matroid. So here we have a birational map between these elliptic modular surface and the realization space of my funny deformed K-gon matroid. And secondly, here we have a lambda operator on this matroid, and we found that on the level of this elliptic modular surface, this corresponds to the multiplication by -2 of that point. So on the elliptic surface, there's this group structure. So we can multiply this point by -2, and this exactly corresponds to the lambda operator we have on the level of the arrangements. So that's the kind of first combinatorial or matroidal model for that surface. And in particular, it's a way of computing the defining equation for this thing. And it's even an integral model because the equations we get from the matroid are all integral.
You had a whole family of lambda operators. You were saying only one of them is really interesting.
Yeah, okay, so I'm saying for the I'm saying that there are a specific choice of NM. I don't want to, I'm sure to now, but for every K, there's one choice of N and M where this works, yes. There's a subtlety for the even case, but at least in the odd case, that's true. And for the even case, we have to make a little trick, but yes. Okay, I have a little bit of time left. Are there further questions? I have a second application also, but the questions to that part.
What kind of gave the connection is basically just the equation.
Yes. We were looking for moduli spaces where we had this lambda operator acting in a natural way. We found that matrix eventually, this for k equals 7. We only later realized that it's connected to the k-gon, to the 7-gon. And then Xavier computed the Picard number and algebraic geometry stuff and figured out that then this what we computed is this elliptic modular surface. And then we kind of got to the k-gon and proved this, that it's birational in general. Okay. So
What is the map?
here, the map? Yes, so the map is rather natural in some sense. So you have this base point and you have the cyclic k torsion. So you take the cyclic k torsion and you take the multiples of that k torsion, you add it up, so that these are exactly k points, which are kind of like a k-gon. And then you apply the lambda operator to these k points. And that's how you get 2 k points. And these 2 k points are the realizations of the matroid. Okay, so let's switch gears. And the second application, I'd like to talk about scattering equations. So these are coming from particle physics. Sure.
From the bottom row, what you're saying is that this lambda operator that you described for a particular choice of element gives you a map from that realization space to the realization space of the same matrix.
Yes.
But so the map, the vertical maps, are they projected?
These maps. These are birational. So yeah, so they mean there's some close. So yeah, maybe I didn't stress it, but so there's some closed exceptional loci, but they're on an open subset. These are isomorphic. In particular, these are not these spaces are not as singular again, but yeah, so you can kind of desingularize it, but take the resolution of singularities, and then there's an isomorphism here.
But then you have to, if you have the lambda operator does what it should on the bottom row. By going.
No, I think we had to prove that this lambda operator does what we want on some subset here. Yeah, and then we later figured out that if you go the other way, then it happens to be the multiplication by -2 here.
So these elliptic modular surfaces have a whole bunch of very nice toroidal compactifications. Do you know anything about compactifications of this moduli space of a matroid? And do you think there could be a connection between natural compactifications there and top and below, or is that?
But there's, yeah, so I talked to Anna Botero in Bielefeld about that, and that's more or less also what she said. And I think it's something which we don't understand yet, but something which will be interesting to understand further. But it's also kind of complicated. I mean, here are a lot of these exceptional loci, and so it's not a very strong connection in that sense. But and the short answer is no, we don't understand yet how these.
So on the bottom line, you can have like several reducible components, right?
Possibly, yes, I suppose.
And then up there you have something that's reducible.
Yes.
So it only needs one component.
I'm not sure, to be honest.
No, it doesn't.
Yeah, but okay, I'm not sure if there can be, if it's irreducible or if it's possible that there are multiple components.
Oh, okay. So
That I'm not sure, but okay.
but yeah, so maybe they also raise the question: what does birational mean if we have several reducible components? Is it birational just one component, or? But we don't know. Okay.
I think in my mind it just meant that we remove some closed subset on both sides, and then we prove the isomorphism on some open subset. But
Okay.
you're right, it's a bit, yeah.
It's a bit shaky in the sense that if we, unless you know that the bottom one is irreducible, then this is perfectly fine, right? But
That's true. Okay, that I'm not sure. I don't know. Thank you. Okay, so briefly in the end, let's talk about scattering equations. So these come from particle physics, where as a sketch, there are particles coming in. There's somehow like a black box where we don't really understand what's happening. There are particles coming out. So on a large scale, that's what's happening in Geneva at the CERN. And for small models, physicists develop theoretical models. And one of these models is the so-called Carchazo-Early-Gerber-Misera model, where they study exactly the realization space of the uniform matroid in some sense. So here they study the space XDN, and which is exactly the realization space of the uniform matroid over C. And in that sense, it's just the modular space of n points in P to the D minus 1, because these are just these the n points are the coordinates of these points are the columns of the realization matrix of the uniform matroid in that sense, and they are all in linearly general position. So the physicists, they'd like to study a potential function, which is it tells them the probability for certain outcomes of the.
To go back to the earlier thing again, for these spaces, there are some very understood compactifications as well. But for the XDN ones, right? This Alexeyev style compactification.
Probably. I'm not aware of that, but
I'm telling you.
Okay. Yeah, that I'd be curious to learn more about this. But for now, so the physicists, they'd like to study the potential function on these spaces. So they take these are again the Plücker coordinates. They take the logarithm, and here these are parameters called the Mandelstam invariants. And so this is a huge function where somehow the key ingredient is to be the logarithm of these Plücker coordinates, and they are all non-zero because we're in the realization space of the uniform matroid, which means that all Plücker coordinates are non-zero. And so when they do that, they like to study the critical points of this equation, meaning that they take the partial derivatives and want to study it. What are the solutions where all partial derivatives vanish? And for generic choice of these US, the number of these critical solutions is constant. It's called the maximum likelihood degree, coming from an analogy in statistics where they all have very similar equations. And then they also study these kind of these critical point equations. And then the solution of this critical points equation is one choice of a maximum likelihood for this statistical model. And Junha proved that this maximum likelihood degree is up to sign equal to the Euler characteristic of that space. So the question of what's the degree of that space is essentially up to sign the same as the question as what's the Euler characteristic of this XDN space. And the physicist, and it's known that in dimension 2, it's n-3 factorial, and the physicists computed these numbers up to n equals 8 in dimension 3. And so in the last step is a result by Daniela Agostini, Taylor, Briszewicz, Claudia Fevola, Bernd Sturmfeld, and Simon Taylor, and we computed the Euler characteristic of that space for 3.9 to be 74,570 in 400. And the way we did that is by some fibration, by where we forget the last column. That's a map from XDN plus 1 to XD. And then the base space is stratified by certain matroid realization spaces. It's not of size 9, but larger, where the picture one can have in mind is the following, that even though these points are linearly independent, there could still be some coincidence happening. Straight blackboard line like this, that the lines generated by these points somehow meet in a extra point which should not happen. And by collecting coincidences like that, these are the matroid realization spaces we find in the base, and then we understand the fibers, and then we can paste together to get the Euler characteristic of this X39 space. Okay, thank you very much.